Hi, and welcome to this lesson on machines. This is a very big building. Let's assume you are standing here and you have to carry these large timber logs to the very top of the building. How would you do this on your own since the timber logs are too large for you to carry by yourself? The obvious thing to do is to find some sort of machine that can help you carry the timber logs to the top of this tall building. This is what we are going to study in this lesson. We are going to take a look at the various forms of machines that help us to do the difficult things in our daily lives. So what do we mean by a machine? Machines refer to things that are created by people to make work easier. They are devices that help to carry out work which would have otherwise required a lot of human effort. Machines can be found everywhere in our lives. For example, in bicycles, vehicles, clocks, and other moving objects. Some machines have non-moving parts such as electronic devices including radio, television, and much more. In this lesson, however, we will be concentrating on machines that cause some form of motion. Machines can vary from each other in terms of the simplicity or complexity. Some involve a combination of very simple parts to form complex machines. A machine can help to increase the effort that is applied by a man or change the direction of an object. We are going to look at 6 main types of simple machines in this lesson. We will look at the inclined plane, screws, wheel and axle, gears, pulley systems, and levers. Let's start by considering the inclined plane. An inclined plane is a type of simple machine. It involves the use of a plane which is placed on two objects that have different heights. When this happens, the plane creates an angle that allows an object to move or to be moved from the lower height to the higher one, or from the higher one to a lower one. In this illustration, you can see that we have a base which is the lower height and then an object which is a higher height. An inclined plane is placed to join the two heights. We then have an object that requires movement from the lower height to a higher height. This object is usually referred to as the load. The load will be made to move on the inclined plane. You can also see that there is an angle that has been formed between the inclined plane and the base. This inclined plane supports the movement of the object from the lower height to the higher height. It means instead of having a person carry the load by himself to that height, we will use an inclined plane to make our work easier. Let's look at some factors that influences the inclined plane. The weight of the object can have an influence on how the inclined plane works. If the load or the object is heavier, it will require more effort to move up the inclined plane. Secondly, the angle of the slope made by the inclined plane can also affect it. This angle is steeper and will require more effort to move the load up to the higher height. The illustration below depicts the second factor that we are discussing. You can see that in the first setup, the angle created by the inclined plane is less steeper than that of the second setup. It means we have a gentle slope for the first setup, and we have a steep slope for the second setup. For the gentle slope, we require less effort or force to move the load up to the higher height. However, for the steep slope, we require greater force to move the slope up to the higher height. Let's look at a few examples of inclined planes in our daily lives. A sloping road is a typical example of an inclined plane. A hill itself can also be an example of an inclined plane. Staircases in our homes also refer to inclined planes. We may also have ramps which help to move objects from the ground to a higher height, say a car, and many more. Let's now consider screws. A screw, technically speaking, is an inclined plane that is wrapped around a pole. Screws help to raise or lower loads or objects. They also help to hold two objects together. A screw can help to generate a great turning force when one applies even the slightest movement or turning. A screw has threads around it which refer to inclined planes wrapped around a pole. These threads help to move the screw a short distance at a time when it is being driven into or out of the load. A screw physically has three parts. It has the head, the threads, and the tip. These all extend from the pole of the screw. Let's look at a few examples of screw systems. We have the normal metal screws that are used to hold two objects together. We have jar lids that have threads around them. We have bottle lids such as the plastic caps and water bottles. We have screw bulbs that have threads to hold a screw bulb in place. We also have bottle openers which have a special form of screw. And we also have drills that have some form of screw bit at one end for drilling into metals or wood. There are several other examples of screws. Let's now take a look at the wheel and the axle, which is another type of simple machines. A wheel and axle is a simple machine that consists of a rod and wheels which move or rotate around the rod. The rotation of the wheel about the rod causes a load to be moved from one place to another. This is a simple example of a wheel and axle machine. You can see the rod and also the wheel that turns around the rod. Take a look at a few examples of wheel and axle system. First of all, we have fans such as the ceiling fan you see here. The blades of the fan are fixed around the wheel which rotates around the vertical rod hanging down from the ceiling. We also have fishing reels that are used to capture fish with a string or coil. The wheel and axle controls are used to extend or coil back the string. We have door hinges as well. A car tire system is another typical example of a wheel and axle system. You can see there is a rod which holds two wheels. We also have paper rolls. Wheel buckets which are tied to a rod are operated by a wheel system, and many more. We now concentrate on gears. A gear refers to a set of grooved wheels that work together by moving each other in order to operate a simple machine. These wheels have teeth on them that they use to connect to each other. You can see on this example the teeth that are used to turn other gears or machine parts. Gears operate when the teeth or one gear are fixed into the grooves of another gear. When this happens and one gear is turned, the other also begins to turn. Gears differ from each other in terms of their sizes, and the turn generates turning power or force depending on the size of the teeth or the gear itself. When the wheels are smaller, they tend to turn more quickly but use less force, while the bigger ones turn more slowly but use greater force. Let's look at some examples of gears. Gears are commonly found in bicycle parts to help power the bicycle. They are also commonly found in clocks and watches. These gears keep the hands of the clock moving at all times. You can also find gears in motorbikes, car engines, mills, and many more. We now take a look at pulleys. A pulley is a simple machine that consists of one or more wheels and a string arranged in such a way as to lift or move loads. The illustration below is a simple example of a pulley that has one wheel and a rope used to lift a load. So note carefully that you need a wheel, the rope, and the load that is lifted or moved. The other end of the rope requires some effort or a pulling force in order to lift the load through the wheel. The wheel of a pulley normally has a groove which holds the rope in place so that when one is using a pulling force, the rope does not sway out of the wheel. As we defined earlier, a pulley system can have one or more wheels that help to lift a load. We can have a one-wheel pulley system, a two-wheel pulley system, a three-wheel pulley system, or even four wheels arranged in order to lift a load. There may be more wheels depending on the size and location of the load that is being lifted. Examples of pulley system in real life include ropes that are attached to the top of flag poles in order to raise the flag, elevator systems which carry people either from the bottom to the top of a building or from the top to the bottom. Pulley systems are used to lower buckets into water wells and then help to pull back the water from the well. Certain gym equipment also rely on the use of pulley system or machines. When you visit a construction site, you may find cranes lifting heavy objects from place to place. They also rely on the use of pulley system. There are many other examples of pulley machines or systems that help to make work easier. We are now going to look at a very important part of our studies on simple machines, which involves a type of simple machine called levers. A lever simply refers to a long solid beam that is placed on a central point known as pivot in such a way that the beam is able to move or tilt to either side because of the pivot. The pivot, also known as the fulcrum, refers to a fixed point around which the solid beam tilts. Let's look at the part of a lever in action very well. A lever, as we said, has a fixed turning point which referred to as the pivot. This pivot allows the beam that is suspended on it to tilt on either side when a force is applied. On one side of the solid beam, a load is placed. That load refers to a solid mass of an object. On the other side, the force that is applied in terms of a push or a pull is what we term as the effort. The distance between load and the central point, which is the pivot, is referred to as the load distance, whilst the distance between the pivot and the point where the effort is applied is known as the effort distance. There are three main classes of levers. These are first-class levers, second-class levers, and third-class levers. Let's now take a look at each of these classes of levers so we can know and understand what they really mean. We start with the first-class lever. The first-class lever is a lever in which the pivot is placed between the effort point and the load. This means the effort or the load is on either side of the pivot. Let's take a look at a typical example of a first-class lever. We have a pair of pliers in this illustration. The pivot, which is represented by a letter P in this diagram, shows the point around which the pliers' load and effort rotate. The load and the effort are on either side of the plier. The effort in this case refers to the side of the plier that we hold in our hands to apply force. Let's look at a few examples of first-class levers. A seesaw that is used by kids on the playground is a typical example of a first-class lever. It has in the middle a pivot around which the solid beam that the children sit on rotates. Another example is a crowbar that is used to remove nails from wood. We also have a pair of scissors that has the pivot in the middle. We also have a pair of pliers as we saw in our illustration. Let's now take a look at the second-class lever. A second-class lever, unlike the first-class lever, has its load coming between the pivot and the effort. In other words, for a second-class lever, the pivot and the effort are on either end of the solid beam. This is a wheelbarrow, which is a typical example of a second-class lever in action. It has the load in the middle, while the pivot and the effort are on either side of the load. Let's take a look at a few examples of second-class levers. A wheelbarrow, as we have seen, is a typical example of a second-class lever. A stapler is also an example. The pivot is on one end while the effort is on another end. We then have a nutcracker. You can see that the load is in the middle with the pivot and the effort on either side of the load. We also have a can opener, which is another example of a second-class lever. Let's look at the final type of levers, which we call the third-class lever. The third-class lever has its effort in the middle, while the pivot and the load are on either side. As you can see in this illustration, we have the effort in the middle. A shovel is a typical example of a third-class lever. It has its effort in the middle, which is where we hold with our hand to use to shovel. We then have the load and the pivot on either side of the effort. Let us look at a few examples of third-class levers. Tongs which are used to pick objects are regarded as third-class levers because we need to hold the middle of the tongue to make it work. This means we are applying the effort in the middle of the tongue. A pair of tweezers used in medical practice is also a third-class lever because the effort is in the middle. A shovel, as we have already seen, is also an example of a third-class lever. We also have a broom, which is another example. Levers can also be found in human beings. More specifically, they can be found in our skeletal system that works with our muscles to cause movement. For example, the human skull together with the vertebral column is a typical example of a first-class lever. This is because it has the pivot in the middle where the vertebral column holds the skull. The load refers to the back of the skull, and the effort refers to the jaw side of the skull. When the jaw is raised up with the help of the pivot, the back of the head tilts backwards. This then shows that because we have the pivot in the middle of the load and the effort, we have a first-class lever in action. Let's look at a different type. When you consider the way the heel works, you find that when you stand on your toes, the muscles behind your leg help you to lift up your heel. Let's consider how this can be a lever and what type of lever it can be. You find out when you tiptoe, you are able to control your standing with the toes. Therefore, that is regarded as the pivot. The load becomes your heel, while the effort is at the back of your leg. So when the effort is lifted up, the load, which is the heel, is also lifted up. This is a typical example of a second-class lever because we have the load in the middle. Let's look at a third example. Assuming we have the human arm, we are able to rotate the arm because the elbow joint acts as the pivot. We are able to rotate the arm because the elbow joint acts as the pivot. The effort can be found in the wrist area, while the load can be found inside the fingers when something is held. When the effort is applied, it affects the load that is held in the hand. This setup is a typical example of a third-class lever. This is because the effort can be found in the middle of the pivot and the load. We now shift our attention to the second part of this lesson, where we are going to learn about work and what it means in science. In science, we define work as the result of a force that is applied to an object, which causes the object to move in the direction of the force. Take a look at this illustration. Assuming we have this plane surface with the load that is about to be placed on it. We need to push this object in this direction so that it will correspond to the direction of the push. When the object is pushed in this direction, it moves from one point to another. This means it has traveled a certain distance. When this happens, we say work has been done. From the illustration we just saw, we can see that a force was applied to an object through a certain distance to give us the amount of work which was done. Therefore, we can define work as the amount of the force multiplied by the distance in which the object traveled. This can be written as W is equal to F times T, where work is measured in joules, force is measured in newtons and distance is measured in meters. So keep in mind that the SI unit for work is joules. Let's look at some factors that can affect the amount of work done in any instance. Work can be affected by the amount of force that is applied. In other words, when we have a greater amount of force, the amount of work that is done will be greater. Take a look at these two examples. The first one shows that the force of 20 newtons was applied on an object through a distance of 1 meter. The resulting work done was 20 joules because we multiply the force by the distance. In another example, a force of 15 newtons was applied through the same distance of 1 meter on an object. The resulting work that was done was 50 joules because we have to multiply the force by the distance. So we can conclude that when we apply a greater force for the same distance, the amount of work that is done will also become greater. Another factor that can affect work is the distance traveled by the object when the force is applied. When the distance traveled increases, the amount of work done also increases. For example, if you apply a force of 1 newton on an object that travels a distance of 10 meters, the resultant work that will be done will be 10 joules because we multiply the force by the distance traveled. Similarly, when we apply a force of 1 newton on an object and it travels a distance of 20 meters, the work done will be 20 joules. So you can see that even for the same amount of force applied, anytime the time traveled increases, the amount of work done also increases. The distance traveled can affect the amount of work done. Let's look at some simple examples of work in real life. When a man pushes a wheelbarrow from one place to another, it means he is applying a force through a certain distance. When you carry a box from one end to another, you are also using force to move the box through a certain distance, and so you have done work. When you use the pulley or a wheel and axle to pull a bucket from the base of a well to the top, the bucket would have traveled a distance because of the force applied. This also means work has been done. When you push an object across the floor or table, work has been done. There are more examples of work in real life. Just remember that it involves the application of a push or pull, which is a force on an object to cause the object to move through a distance. Let's now take a look at a topic related to work, which is energy. The definition of energy is simple. It simply refers to the ability that we have to do work. In other words, it refers to the ability that we possess to apply a force on an object through a distance. This is the energy that is acquired from the food we eat from plants and other animals. The energy helps us to carry out the intended work. If we have energy, we can apply force. If we have energy, we can push or pull objects over distances. This is what is required to do work. If a body does not have energy, it cannot push or pull an object through a distance. This simply means work cannot be done. Just like work, the SI unit for measuring energy is given in joules. Power is our next topic in this lesson. Power simply refers to the rate at which work is done. In other words, it refers to the rate at which we transfer energy from one thing to the other. Another definition for power means the amount of work that we do within a given period. Mathematically, we can say power is given by W divided by T, where power refers to the rate of work and is given in watt. W refers to the work that is done, and this is normally given in joules. T refers to the time or the period in question. Take note that the SI unit for power is given in watt. We are now going to look at a very important aspect of our study on machines, which involves using various mathematical methods used to evaluate simple machines. We are going to look at how to calculate what we call the mechanical advantage, velocity ratio, and efficiency of machines. We start with mechanical advantage. Mechanical advantage, also written as MA, is the factor by which a machine multiplies applied force. The mechanical advantage of a machine can be used to find out how well a machine works and whether it can perform a particular job. Mathematically, we can find the mechanical advantage as the load force divided by the effort. We will expand on this formula pretty soon. But for now, let's look at velocity ratio. Velocity ratio of a simple machine is the ratio of the distance traveled by the effort to that traveled by the load. Mathematically, we can write this as the effort distance divided by the load distance. The effort distance, as we said earlier, refers to the distance between the effort point and the pivot, and the load distance refers to the distance between the load and the pivot. The third one is the efficiency of machines. Before we go on to study what efficiency of a machine is, we need to consider two things. The first one is the work input, while the second one is the work output. The work input is work that is done when the force of the effort is applied to the machine. This can be obtained when we look at the distance traveled by the effort when the effort force is applied. Let's take a look at a few illustrations so we can better understand this. Consider this simple first-class lever which has the pivot in the middle. The load and the effort are on the other ends of the solid bar. When the effort is applied on the bar will travel a distance because of this force. This means when we multiply the force which was applied by the distance traveled, we will find that some work is done because of the effort. This work refers to the work input because it considers the input force that was applied. Let's take a look at another example. This time, we will consider a one-wheel pulley system. The effort is applied by gripping the rope and pulling it with a force. When this happens, a distance will be traveled because of the pull on the rope. We multiply the force of the pull by the distance traveled by the pull. We obtain the work input. Let's now consider the work output. The work output refers to the amount of work that is done when the load moves through a certain distance. The load is able to move because of an input that is applied. In other words, it is able to move because of an effort's push or pull. Let's once again use a simple illustration to understand this. Assuming we had this first-class lever setup with the pivot in the middle, whilst the load and effort on either side of the solid bar, when we apply an input force, an output force forces the load to move upwards because of the rotation on the pivot point. This means the load would have traveled an upward distance. So when we multiply this output force by the distance traveled by the load, we obtain the work output. Let us consider the work output for a one-wheel pulley system as well. Once again, we can see that the effort is used to apply an input force, which means the effort is used to pull the rope suspended on the wheel. When this pull is made, the load is able to move upwards due to an output force. The load then travels a distance due to this. When we multiply this distance traveled by the output force, we obtain the work output. So now we can go ahead and try to define the efficiency of a machine. The efficiency of a machine is a measure of the amount of output that is obtained as per the input given. It tries to measure how much work or energy is conserved in the process. If a machine does not lose any energy when working, it means it is working as a perfect machine. Therefore, we say the efficiency of a perfect machine is 100%. This is usually not the case in most machines because whatever happens, some energy is lost. When energy is lost, the efficiency of a machine becomes less than 100%. The loss of this energy is due to a variety of reasons. When friction occurs between two parts of a machine, it means some of the energy is taken up from the input energy. When two machines or machine parts are involved in some activity, some of the energy gets transformed into other energy forms such as heat and sound. This heat and sound may not be desired, and therefore we say they represent the lost energy. When a machine is being opposed in terms of how it works, we may need to apply more input energy into overcoming that opposing force, which may be the force of gravity or the force of friction. When this happens, we may have used too much input energy than what is required to give out to the output energy. Let's look at ways by which we can calculate the efficiency of a machine. As we mentioned earlier, the efficiency of a machine measures the output against the given input. So mathematically we can say the efficiency of a machine is equal to the work output divided by the work input times 100%. We know the work output to be defined as the load force times the distance traveled by the load. We also know that the work input measures the force applied by the distance traveled by the force. So our mathematical expression can be expanded as seen here. Another way by which we can measure the efficiency of a machine is to divide the mechanical advantage by the velocity ratio and multiply it by 100%. Take note of these formulas very carefully. Let's now look at the last section in our lesson today, which considers complex machines. A complex machine refers to a machine that is made up of two or more of the simple machines we have looked at. They may sometimes be a combination of two separate types of simple machines, or simply several simple machines of similar type. In the example below, you can see that we have a nail clipper which has several simple machine parts. Take a look at the second image. You see that we have a lever, which is a simple machine type. However, we also have another lever which also works in a separate fashion. Consider this bicycle. The bicycle has several parts that can be categorized as simple machines. However, these simple machines have been put together to form a complex working bicycle. For example, we have screws that hold various parts of the bicycle together. We also have the wheel and axle, which refers to the tire wheels and also the pedals. We also have a pulley system that is used in the braking mechanism of the bicycle. We also have gears which have rotating teeth to keep the chain of the bicycle moving when it is being paddled. There are several parts of a bicycle for which you can take time to study. Other complex machines include tractors, ships, sewing machines, cars, blenders, cranes, etc. It is important to oil various parts of machines that have frequent contact with others. This ensures that there is less friction and also less wear and tear. Friction can also be reduced between machine parts by polishing or smoothing the surfaces. Regularly, it is important that we check between these parts to remove dust or any unwanted material that may cause wear and tear or affect the efficient functioning of the machine. When there are parts that are weak or worn out, it is important to remove them and replace them with new ones so that they don't end up damaging the other part. We should also ensure that screws, bolts and nuts, rivets and nails that hold two or more parts together are always tightened to prevent these parts from dislocating and causing damage. This has been a very long lesson on machines, but I hope you have found it useful and have also enjoyed it. I hope you join me in the next lesson. Goodbye.